Hello. We're going to talk about what it means for a set of vectors in S to be linearly independent. Essentially what it means is I can't write any vector in S as a linear combination of the other vectors in S. So that would mean that they are linearly independent. To take a look at these, sometimes we can use our intuition. Like for instance, are the vectors -1, -1, and 2, 1 and R2 linearly independent? Well, I have them plotted over here, and remember when we took a look at our previous video, we were looking at linear combinations of these to get another vector, but really we're looking at these in terms of, can I write one as a linear combination of the other? And with two vectors, it's really easy to see that if one is not a multiple of another one, then I can't write this as a linear combination of the other. So what that means is, yes, that these two vectors are linearly independent because I can't write one in terms of the other. So yes, these are linearly independent because I cannot write one in terms of the other. And with two vectors, it's pretty easy to see. You can also use your graphical intuition approach. But sometimes intuition and graphical nature sort of eludes us. So let's take a look at another example here. Example 2 would be a set of vectors in R3. So we're talking about space now. So are the vectors in S linearly independent? Well, you might notice if you're careful that if I took -1 of the second vector plus the third vector, I would actually get that first vector. So if I took -1, I have -1, which is 1, -2, which is 2, and -1, which is 1 plus 2, that's 3. So in this case, no, these are not linearly independent. But most likely we couldn't see that right off the bat. So what's a nice way to tell if something's linearly independent with what we know so far in the class? Well, how do we know if a set of vectors S are linearly independent? What we can do is we can write a system of equations where we take constant multiples of those vectors in S. So this is a linear combination like we studied in the other video, and set those equal to the 0 vectors. If we only get the trivial solution for this system, then that means the only way we can write a combination of these vectors if we have 0 times each one of these is equal to 0. So there would be no way we could express one in terms of the other. Let's make it clear that since this is a homogeneous system, it will always have a solution. If it has that trivial solution, then they'll be linearly independent. If it doesn't have just a trivial solution, we would be able to express any one of these vectors in numerous ways in terms of the other ones. So let's go ahead and revisit the examples above. So the first thing we're going to do is set up that system of equations, that homogeneous system. So C1 times the first vector plus C2 times the second vector is equal to 0. And we can convert it into a matrix equation by the matrix vector product. And I'll just use REF. And it turns out that we only get the trivial solution here. So C1 has to equal 0 and C2 has to equal 0. So in this case, I cannot express the vectors in S as a non-trivial linear combinations of each other. So what that means, of course, is we know that, yes, the vectors in S are linearly independent. And we saw that in our first step, but this shows it in an easy way, sort of algebraically. Let's look at our second example again. So again, we set up that homogeneous system here. In this case, we're in R3. We use the matrix vector product to turn it into a system. And I'll just go ahead and use my REF as I always do. It turns out since we have a row of zeros that there's a free variable here, so C3 is free, and I can express C1 and C2 in terms of that C3. So if I turn this back into a system, it looks like this. C3 is free, and then I translate it over. So C1 is equal to negative C3, C2 is equal to negative C3, and C3 is equal to itself. So this implies there's a non-trivial solution, so the set is not linearly independent. In fact, if I wanted to write one in terms of the other, there's infinitely many ways I could do this. But one thing I could do is let C3 be 1, then I would have negative 1 of the first plus negative 1 of the second plus 1 of the third is equal to that 0 vector. And for instance, I could express this third one in terms of the first two by just adding those two over to the right. So now I have that third vector is equal to 1 of these plus 1 of those. And we showed that they're not linearly independent because I can write one in terms of the other. Okay, well, I hope this has helped. Thank you.